We started this semester with the concept of motion. Then we went into more detail with speed. And then we looked at how to change speed, and that was connected to force. And then we found out how force is related to the concept of momentum. If you noticed in chapter 8, we started with rotational motion, and then we moved into rotational speed specifically. And then we discussed the quantity of rotational force, otherwise known as torque. So that brings up a natural question at this point. Is there rotational momentum? And the answer is yes. It's commonly referred to as angular momentum. So we're going to talk about angular momentum now. I should point out that angular versus rotational, they're commonly used back and forth. So you could say angular motion or angular speed or angular force. Those words are interchangeable. But for momentum specifically, most people call it angular momentum. So as a reminder of momentum in general, that was just mass times the velocity of the object, or mv. And I didn't mention this at the time, but you can think of momentum as the inertia of motion. What I mean by that is the more you try to change momentum, the more difficult it becomes. Angular momentum has that same property. It's just a rotational version. So what we can say then is that angular momentum is like the inertia of rotation. The more you try to change rotation, the more difficult it becomes. Up here for our definition of momentum, when we said mass of the object times the velocity of the object, if you remember, mass was a physical representation of inertia. If angular momentum is just the angular version of momentum, then really all we need to do to define angular momentum is take the rotational versions of these quantities. So we can define angular momentum as the rotational inertia and the rotational velocity. Symbolically, we use I for rotational inertia and omega for rotational velocity. Remember, this isn't a W, even though it looks like it, it's the Greek letter omega. There's some other similarities we can look at between momentum and angular momentum, and this just saves us from redescribing angular momentum from scratch. So with regular momentum, I talked about how momentum changed with external force. But if no external forces act on the system, the total momentum is conserved. Remember, the system is just a group of objects, or the group of objects you happen to be interested in. So we can say then that angular momentum changes with external torque, because that's just the rotational version of force. Likewise, if no external torques act on the system, the total angular momentum is conserved. We spent a lot of time looking at momentum and how it changed with external forces. That was the force-impulse relationship, where the change in momentum is equal to the contact force multiplied by the contact time. There's a similar process for angular momentum using torques, but it turns out that if we're not going to go into the mathematics of these two quantities, then there's really not a reason to do that at this point. We're going to take more of a conceptual approach, and let's just focus on situation in which angular momentum is conserved. So that means there's no external torques that would cause our angular momentum to change. So in that case, whatever you started with, so this is our initial angular momentum, that should be equal to whatever you end with. That's our final angular momentum. Let's look at some specific examples. Okay, so here let's just assume some value for our rotational inertia and for our angular speed or angular velocity. And I want to consider a situation where the rotational inertia has increased. And I'm using that notation our textbook likes to use, where they just show a bigger I, meaning bigger rotational inertia. Well, if this increases and momentum is conserved, or angular momentum is conserved, then what would happen to my rotational velocity? It must decrease so that this equality still holds. Now, let me maybe use some numbers for this. So I just made up some numbers. So assume that the rotational inertia is 3 and the rotational velocity is 6. Okay, well, together those quantity that equals 18. So we can say that our initial angular momentum is 18. Whatever is over here, we need that to equal 18. So let's say that we increased our rotational inertia to 9, which means it tripled. Well, in order to protect this ratio, that would mean my angular velocity here has to decrease by the same factors, so it would be cut to a third, which would be 2 in this case. So the product of these two quantities is still 18, just like it was before. But what you're really seeing is that if one increases, the other has to decrease by the same factor. Now let's consider a different situation. What if I decrease my final rotational inertia? Now how I would do that is I would remember that rotational inertia depends on total mass, and the distance mass is located from your rotation axis. So I could decrease my moment or my rotational inertia by bringing the mass closer to the rotation axis, or just simply decreasing my total mass, or some combination of that. So let's say I did that. How would that affect the angular speed? Well, that would have to increase by the same factor to compensate. So here I'll use different numbers. So let's say I started with 4 and 3, so together they make 12. And then I cut my rotational inertia to 2, so I cut it in half. That means I have to double my angular speed. So together they still equal 12. Okay, over here, an example of increasing your moment of inertia would be to either move more mass away from the rotation axis or to simply gain more mass. Let's maybe do another practical example. So here I have somebody spinning and they're holding some weights out to the side. So they have some rotational inertia and some rotational speed. Together that's their initial angular velocity or angular momentum. And then we want to consider the situation that if he pulls his arms in, that should decrease his rotational inertia. What will happen to his rotational speed as a result? Okay, so symbolically it would look like that, where I have a smaller I. And what we just talked about is that would mean that the omega should get bigger. Or in other words, he should rotate faster, so something like that. And this really does work. Here's an actual example. So here's Bella, and she's holding some weights. That will allow her to change her rotational inertia. If she decides to move the weights outward, then she's moving them away from the rotation axis, which is going to be just a vertical line here. She's going to spin around this chair. So the rotation axis is just this vertical line. So if she increases her rotational inertia by moving the weights outward, that should decrease her speed. Let's watch that. Okay, so you can see how she slowed down, but then when she pulled them back in, she just sped right back up. So remember, the angular momentum is conserved, so it doesn't disappear. So she can control how fast she goes simply by moving the weights outward or inward. All right, here's a slightly different situation. What if she takes these weights and she moves them, she lifts them straight up above her head? How will that change the rotational inertia? Why don't you think about that? All right, if you said that it increased, we need to think about that a little closer. So the rotational inertia doesn't care about the distance of the mass from the center of mass. So yes, if she lifted it up, she would be moving the center of mass, or the distance from the center of mass. All rotational inertia cares about is the rotation axis. So the rotation axis is just this vertical line. So if she lifts these weights straight up, she's not actually moving them away from the rotation axis. So she's not changing her rotational inertia. Therefore, her angular velocity or rotational velocity should not change. Okay, let's watch that. Okay, notice the spin isn't changing, although when she pulls them out, there's an obvious effect, and then back in, speeds back up again. Okay, that's an example of conservation of angular momentum. I want to go back to our definition of angular momentum and highlight the fact that its rotational velocity is a vector. So if angular momentum is defined by a vector, then it itself must be a vector. That's important because that means that angular momentum cares about direction. So if we're going to say that angular momentum is conserved, then that also means that the direction of the angular momentum must not change. If the direction changed, then the vector changed and it would not be conserved. Angular momentum direction is a lot more complicated than momentum direction. So we'll try to simplify it down as much as we can. Here I have a wheel, and when it's not spinning, it doesn't have any angular momentum. So there's really nothing to conserve as far as angular momentum or regular momentum for that matter. So watch what happens when I try to balance it like that. I mean, technically I should be able to balance it. We know about stability if I can get the center of mass right above the support point, but that support point is just this tiny little dot, so that's pretty difficult. All right, but if I spin this wheel, then suddenly it has angular momentum. Okay, so imagine this is spinning now. The direction of the angular momentum, like I said, is a little complicated, so I don't want to explain it completely. But for this spinning wheel, it turns out that the direction is up. Okay, gravity, we know, should be right there. And remember, this is a symmetric wheel, so the center of mass should be right there. So gravity is going to act right at the center. And this right here, the handle, is the rotation axis for the wheel. So if you remember our discussion of torque, the moment arm, is actually 0 because the gravity is acting at the center of mass, which is on the rotation axis. So what I'm really trying to say is that torque due to gravity is 0, so angular momentum should not change. In fact, and what that really means is the direction here should not change. This vector should always be pointing up. Okay, so watch what effect it has now that I spin the wheel and try to balance it. You can see an obvious difference in how it behaves. Now it's not perfectly free of any external torques. That's why there's a little bit of wobble there. There is drag and there is the interaction with the table. So it does wobble a little bit, but it's much, much more stable, as you can see. Well, it turns out that this conservation of angular momentum isn't limited to just horizontal wheels. What if I try to spin the wheel vertically? Well, first of all, if it's not spinning, there's no angular momentum, so there's nothing to conserve. So in this time, I've got a string attached to one of the ends, and I'm going to try to balance the wheel just about that string. Well, just watch. Okay, so no surprise, it just falls over. There's no reason why it would stay up. So when I was in the previous situation here, gravity is right there. So it's pulling it down. The lever arm would be like that because the rotation point is right there. So gravity is some distance away from the pivot point. It should be applying a torque, which is why the rotation of the object changed. So that's just an application of gravitational torque. Now, if I spin the wheel, the direction of the angular momentum is going to be that way. Gravity is still acting straight down. So as far as the rotation of the wheel itself is concerned, there's no torque due to gravity because gravity's at the pivot point for the wheel. However, that's just the wheel itself, where the rotation axis is the handlebar here. There's also another possible location for rotation, and that's right here. Highlight that. So that is a possible rotation point. So there's two different ways you can get torque in this case. So gravity, there is a lever arm, it's not zero. And in fact, gravity would be perpendicular to that lever arm. So we should be getting the maximum torque relative to this point. So in other words, it wants to rotate the wheel, but now that it has angular momentum, that angular momentum does not want to change. So you can think of it as the angular momentum is going to fight the change that gravity is trying to apply at this pivot point. I'm going to spin up the wheel and let's just see what happens. So the angular momentum vector does not want to change, so it's trying to oppose the effect that the gravitational torque is applying. The practical application for that is, of course, just this. Bikes are easy to ride as long as you're moving. That's because the wheels have angular momentum, and the direction is trying to stay constant. But as soon as you stop and try to balance on one, you'll find that it's much more difficult to stay upright. All right, this is our last example. I'm doing the same thing I was doing in the example for centrifugal force. I just have an object tied to a string and I'm spinning it around. But instead of letting it go and having it fly off, this time I'm going to stop spinning and I'm going to hold out my finger so the string will wind around my finger. Now watch what happens. When I stopped the hand motion that was actually spinning up the object, the rotation should have started to slow down. But what we saw was that it actually kept going, and in fact it increased, especially the end. It really increased. So let's just watch that one more time. You see how it's speeding up right at the end especially? Okay, so why would it speed up when it should actually be slowing down? Well, it's just conservation of angular momentum. In this case, I've changed the rotational inertia by shortening the string, or in other words, I was bringing the mass closer to the rotation point, the rotation axis. That decreased the rotational inertia, so the rotational speed had to increase in order to conserve angular momentum. At the end, the string became really short, so the rotational speed had to get really large. Hopefully that was enough to at least give you an introduction to the concept of angular momentum. This also concludes our discussion of Chapter 8 on rotational motion in general.